Welcome to this video on Hess's law. Our big question is, how can we calculate enthalpy changes indirectly? And in this video we're going to introduce the concept, help you to understand Hess's law, and we're going to talk a bit about enthalpy cycles. So let's begin. Some enthalpy changes are relatively easy to measure. This neutralization reaction between hydrochloric acid and sodium hydroxide can be followed by a method called solution calorimetry, which we've covered earlier in the topic. And the essence of this method is that we take the chemicals which are dissolved in water, we mix them in a polystyrene cup as shown here, and we measure the temperature change on a thermometer. For other reactions, such as the combustion here of methanol, we can use a slightly different setup where we contain our reagents in this glass spirit burner here. We burn the fuel, and then rather than having the water in the same place, we actually put some water separately in this copper can, and again we measure a temperature change, delta T. Now in both those cases we're able to then turn that temperature change into the enthalpy change for the reaction. However, in some other reactions it's very difficult to do this. For example, if we look at this thermal decomposition of calcium carbonate here, we find that the reaction rate is far too slow in order to be able to measure a temperature change in a reasonable period of time. And typically if we want this reaction to happen, we have to use a setup like this, where we use a Bunsen burner to heat a test tube containing the metal carbonate, and then we can detect the carbon dioxide produced by bubbling it through lime water. Unfortunately, if we try to use this method to determine the enthalpy change, we're going to run into problems. Because if we're trying to heat something, then we're going to be finding it very difficult to accurately measure the amount of temperature change occurring in the metal carbonate, because we're applying a huge amount of heat in order to get the reaction to take place. However, we still want to know the value of the enthalpy change, so we need to use a slightly different tack. So I'm just going to illustrate this here on this diagram by imagining that the initial state that we want to start off with is A, and we want to try and find the enthalpy change that occurs on going between A and B, and I'm going to call that here delta H. Now let's say that we don't know the value of delta H, but we do know that if we start in state A, we can actually determine the enthalpy change directly to go to state C, some kind of intermediate state here, and we determine that that value there is minus 50. Let's say we're working in kilojoules per mole, but I'll leave the units off for clarity. And we also happen to know that if I want to go from state C up to state B, I can do that, and I can measure from experiment that my enthalpy change for doing that is plus 90. Now it'd be worth taking a moment here just to pause the video to think, what do you think the value of delta H will be? Well, from the picture, hopefully you can see that delta H here is going to be equal to the sum of those two enthalpy changes, minus 50 plus 90. So it comes out to be plus 40 in whatever unit we happen to be working in. Now let's see another example here on the right. Imagine that we want to go between A this time and another state X. Now I've left X off here because we don't know exactly where it's going to be, but we know from A to D, for example, is plus 20, that if we want to go from D to E it's minus 30, and then if we want to go from E to X it's another minus 40. So we're going to see here that X is, let's make that arrow a little longer. The X is somewhere down here now, and if we extend the arrow across, we're going to see that there's our delta H now. This is X down here. This was minus 40, and so we can work out delta H again. This time we've got to go up by 20 first to get to D, down by 30 to get to E, and down by another 40. And so we find here that we've got minus 50 this time as our enthalpy change. Now why the two examples? Well, hopefully what you've seen from the two examples is that this sort of procedure where we have these two routes, either the direct route shown here, or the indirect route via an intermediate, or in this case several intermediates, will yield exactly the same enthalpy change. Now the reason for showing you both examples was to show you that actually the number of steps in these two routes doesn't actually matter. You can have two routes with one step and then two steps. You can have one step and then three steps. You could have 5 steps and 7 steps. As long as you've got two routes between the same starting and ending points, the total enthalpy change will be the same. And that is known as Hess's law. It's a manifestation of the conservation of energy, and it's fundamentally true because the enthalpy change is determined by the enthalpy of the products subtracting the enthalpy of reactants. Now, in thermodynamic language, enthalpy is known as a state function, which means that it only depends on the states that you are in. So if you are in a particular state, let's say B, you have a certain enthalpy. That's why we can draw it on this enthalpy level diagram. This is the enthalpy of state B. And this is the enthalpy of state A. And the enthalpy change is simply the difference between the enthalpy of B and the enthalpy of A. And it doesn't matter what path you take to go between A and B, as long as your starting and ending points are the same, you would expect exactly the same enthalpy change. So let's try and now make use of this. This is Hess's law stated. Again, the enthalpy change between two states is the same, no matter what the route is between them. It's named after a man called Germain Hess, a Swiss-born Russian chemist and physician who published it in 1840. Now, how can we go about using it? Well, the first thing to note is that the energy level diagram that you can see on the left-hand side, which we've been using to illustrate Hess's law so far, is rather cumbersome. Now, we do use this sort of representation when we use Hess's law to solve problems involving the formation of ionic lattices, known as the Born-Haber cycle, and we'll see that in Year 13 chemistry. But this is actually quite a difficult diagram to use in these problems, and it has a certain number of problems. The main two are that we need to somehow do this to scale if it's going to be useful, and probably the most difficult is that we don't really know where to put our final state on until we've actually calculated all the enthalpy changes. So actually instead what we're mainly going to work with in this topic, in fact exclusively, is what's known as a Hess cycle. And this is basically as drawn here. We've got our three states, and instead of having an energy axis here, we just simply connect the states together where there's a reaction between. So in our case here, we had our direct energy change, which was delta H, and then we also had our various indirect ones. So A going to C, we said was minus 50, and then C going to B was plus 90. Now once we have it in a cycle like this, it enables us to see two routes between the start and finish points. So if we have a look, there will be a point where both arrows start, and that is known as our starting point. And then we can also see another point here, if I just pick a different colour, where both the arrows will end, and that's our ending point. Now we can then from this see two different routes. We can either go on this route here, which is the red route, or we can go along the blue route, which goes again from the same starting point to the same finishing point, and yet we can go via C. Now Hess's law tells us that we would expect that the enthalpy change along the red route, which I'm going to call route 1, should be equal to the enthalpy change along route 2. Now another way of looking at this as we finish is just to see that actually if you look imagining that the middle of your energy cycle is like a clock. So there's my hour hand and there's my minute hand. I won't draw this on in the future, but just imagining that we've got a clock face running around here like this. if you look carefully at the red arrow, you can see the red arrow is pointing in a clockwise sense. It's like this, it's going around the clock that way. Whereas the blue arrows are actually pointing in the anti-clockwise sense. You can see they're both pointing in the same sense, but they're going anti-clockwise. So another way of thinking about Hess's law is to say that rather than thinking about routes between starting and ending points, we can simply say that the sum of the enthalpy changes in the clockwise direction has to be equal to the sum of the enthalpy changes in the anti-clockwise direction. So another option, if you don't like identifying the routes between the two states, is to look at which arrows have an anti-clockwise sense and which arrows have a clockwise sense.